Okay. Okay, welcome everyone to this new IFIMAC and ICMM online seminar. Today our speaker is Professor Timur Shegai. So let me start with a brief introduction to this good friend. Timur is an associate professor in the Department of Physics of Chalmers University of Technology in Gothenburg, Sweden. In 2003, he graduated in Novosibirsk State University in Russia, after which he moved to Israel to continue his postgraduate studies in Weizmann Institute. In 2008, he finished his PhD on single molecule spectroscopy and plasmonics, and shortly after, he already moved to Chalmers as a postdoctoral researcher. In 2012, he obtained a prestigious Young Investigator Grant from the Swedish Research Council, and since 2017, he is a faculty member in the university and is the head of the experimental group working on strong light matter interactions and semiconductor 2D materials. Timur's interest, if you look at his webpage, Timur's interest lies mainly in these two topics, but more specifically on plasmon-exciton interactions, surface-enhanced phenomena like SERS or fluorescence, quantum and low-temperature plasmonics, directional antennas, plasmonic nanowires, and sensing. And it is remarkable, apart from all these broad different topics, that in his group, they operate with techniques ranging from single molecule, single particle spectroscopy, angle resolved Fourier imaging, nanofabrication, different nanofabrication capabilities, and electron microscopy. And he is going to talk us today about strong light matter coupling, from transition metal dichalcogenides to Casimir self-assembly. So Timur, please, and thank you.
Thank you, Antonio. I hope everybody can hear me well.
Yes. Yes.
So thank you very much for a kind of introduction and also for the opportunity to speak. So as you see, the title is kind of broad. It encompasses two of my research interests, TMD materials, transition metal dichalcogenides, and strong light matter interactions. So actually, it will be a blend of different stuff that you will hear today. And yeah, I will kind of try to give you an overview of what our lab is doing. But if I don't have enough time, maybe you could be interested to visit my Google Scholar profile or the group webpage to learn more about a topic which could be interesting for you. Okay. So I would like to start with acknowledgement to the group members. Specifically, most of the stuff that I will be speaking about today is done by these four people, Batulga Munhpat and Denis Baranov. Batulga and Denis, they were really bright postdocs in my group. Now both of them left, and both of them are assistant professors at various universities. So I think they have a really bright future. Adriana Canales is a PhD student whose work I will present, and Betul Kuchikos is also a very talented postdoc. She contributed to most of these projects. Also, I would like to acknowledge collaboration with Andy Yankovic and Eva Olsson and Matthew Kocek on the electron energy loss spectroscopy, and on TDDFT project, I would like to mention Thomas Rossi, Paul Earhart, and Tomasz Antusevich. Also briefly acknowledge grant agencies, and even some stuff that I will be speaking about today is actually in this startup company, which we just started. Maybe some of you might be interested in that. All right, so I will be speaking about strong coupling, and I just want to say that it is a rather generic phenomenon, and it can be really realized in very, very different systems. I was not really sure like who are exactly the audience, so I will try to keep it kind of simple. And maybe just to give a very brief introduction, I would like to say that what we require in the cavity emitter strong coupling scenario, and this is a generic picture which you can see here. You can imagine that you have some kind of cavity, yeah, and that cavity, some kind of optical cavity, yeah, it can be a Fabry-Perot cavity or plasmonic nanostructure, or maybe a DBR cavity or something like this. And this is coupled to an emitter, quantum emitter, for example. And what I mean by cavity emitter strong coupling is that the coupling strength G between the emitter and the cavity can become bigger than the cavity and emitter dissipation rates. And this is when we enter the strong coupling regime. So in my talk, I will briefly speak in part one about plasmonic structures, where this generic cavity is kind of a plasmonic nanoparticle. And in part two, I will also speak about Fabry-Perot cavities, where these two mirrors are then really represented by macroscopic mirrors. But this will be not only scenario which I want to consider. Actually, in the final part of the talk, in the third part, I will speak about 2D materials more generically. And here, I would like to discuss with you something called what we like to call self-hybridization or cavity-free concept. In this idea, basically the idea is that the cavity and the emitter in this case are represented by the same material. How is this possible? It is possible if the background permittivity of this material, this can be some, for example, HBN or 2D material, something like this, some other 2D materials. In particular, in my talk, I will mention transition metal dichalcogenides. So they actually have very, very high background permittivity. And that means that if you create a nanostructure made of this material and place it in vacuum, it will already, just because of its background permittivity, support its own optical modes. It can be Me resonances, it can be Fabry-Perot resonances, it can be various kinds of whisper and gallery modes, for example, depending on what exactly your structure is. All right? So this is due to background permittivity. But if this material simultaneously supports solid state excitations, for example, excitons or phonons, and you're able to tune your kind of optical mode sustained by that structure to the position of the exciton or of the phonon, then what you can expect is hybridization between this optical mode and this solid state excitation, occasionally leading to actually polaritons. Similar to this case, but maybe with an advantage that fabrication can be much simpler. Here, you don't really need to construct any separate cavity, any separated emitter. You just create a material, your nanostructure material itself, and if it supports, let's say, high enough oscillator strength transitions, then it will actually automatically support polaritons. So actually, one of the interesting concepts, which actually I don't understand myself right now, is how these two worlds are related to each other. Like, what are the differences between them? What are the similarities between them? And where one or another can have advantage? I think it's not entirely clear, at least for me. So I would like to share this with you and see what you think about this. So let me start briefly with part one. And actually, this is one of a few theoretical works that we have done. So here, I would like to discuss the single plasmonic nanoparticle, and this plasmonic nanoparticle would be small enough to be treated from first principles from ab initio using time-dependent DFT approach, density functional theory. So this was done in collaboration with Thomas Rossi, Paul Erhardt at Chalmers, and Tomasz Antosiewicz at the University of Warsaw. What we have done, we have taken aluminum cluster consisting of just 201 atoms. And we choose aluminum because it doesn't have d electrons. So it's relatively simple to calculate with TD-DFT. And this structure actually alone already supports a plasmon resonance, which you can see here in about 7.5 electron volt range. Yeah, this is where it is. So interestingly enough, just 201 atoms is already enough to have collective excitations in the plasmon form. And then we just needed to think about a molecule which would be overlapping spectrally with this plasmon. And funnily enough, just a simple molecule as benzene, so very standard molecules in quantum chemistry calculations, actually has a resonance at around 7.2 electron volts, close to the resonance of aluminum cluster. So then we mix them together, and we actually get a familiar Rabi splitting. So a spectroscopic result of strong coupling when there is a hybridization between, let's say, molecular resonance and the cavity resonance, is the splitted like spectrum where you have new eigenmodes of the system, which are symmetric and antisymmetric mixture of, let's say, in this case, molecular and plasmonic excitation. But because we have treated this system from the TD-DFT perspective, we actually know much more detail about this. For example, we know that the low polariton would look like this. whereas the upper polariton would look like this. And you can see actually even the symmetry conditions which can be fulfilled here. Here, what you see in the center is aluminum 201 cluster, and these two molecules are two benzene molecules. So what you can see, this blue and red color here is kind of representation of a phase. And what you can see here is that, for example, this one is blue, red, blue, which means that there is a certain phase relation between molecular excitation and the plasmon excitation. But if you look here down, it would be blue, blue, red. So you see, this is blue, red, blue, and here this is blue, blue, red, right? So this corresponds exactly to symmetric and antisymmetric mixing of cavity and emitter excitations. And but in a way, we kind of provide much more detail about this strongly coupled system, really from the first principle perspective using TDDFT. From the point of view of material, it's actually quite nice, right? Because we do not, we treat material to a rather high level of accuracy. From the maybe quantum optical perspective, there is no quantum optics here, so to say. So it's a quantum, this is classical optics. But from the material perspective, everything is atomistic here, right? So we get a lot of information. And actually, one thing perhaps to mention, which is rather cool, is that you see there is a lot of information that we can get here about the excitation in this plasmon. And it actually looks quite different in the low polariton and in the upper polariton. You see there is a lot of structure over here, which one could dig in even further and perhaps even try to use this model system to get some insights, maybe even about polaritonic chemistry in strong coupling regime and things like this. Okay, so what we have done further with this work, we have looked into collective effects and into particle size effects. So by collective effects, I mean that we looked into different number of benzene molecules coupled to that cluster, going from 1 benzene molecule to actually 8 benzene molecules. It's not really a high number, but this is what we could track with the TDDFT. And then we actually saw that the collective coupling strength was actually just proportional to the square root of n, where n is the number of benzene molecules in this case. So essentially reproducing the good old result from the Tavis-Cummings Hamiltonian in the quantum optics regime, but here actually reproduced from the ab initio perspective, right? And you can see that Rabi splitting increases as you increase the number of molecules. So it is kind of the collective effect is captured by these formulas. Then we have also increased the number of atoms in the aluminum cluster, going from 201, then 586, then 1289. These numbers correspond to the proper icosahedra form of the aluminum cluster, such that it is conserved sort of shape-wise. That's why these strange numbers. But what you can also see is that Rabi splitting actually reduces for bigger and bigger cluster because seemingly the kind of the localization of the optical mode is harder with a bigger cluster. So this is what we saw then, that for 201 atom aluminum cluster, we get a stronger coupling per molecule. Actually, per molecule is a rather big number. Even for a single benzene molecule, we can get coupling strengths on the order of 200, even more milli-electron volts. That's a very big number actually for a single molecule, if you consider. But then don't forget that we are here working at around 7 electron volts, which means that actually with a single molecule, we're still rather far from things like ultra strong coupling, even despite the fact that this 0.2 electron volts is like a gigantic number for a molecule, right? But actually a little bit of maybe kind of spoiler. Actually, at the moment, we do work on ultra-strong coupling with individual molecules, following up on this work. And what we are doing actually is looking for a dimer of aluminum structures with a small gap in between and then placing a molecule there. This is done in order to confine the optical mode even further beyond what this individual molecule can do, individual particle can do. All right, so this was a kind of my glimpse to just the first part where we speak about plasmonic nanoparticles. We do a lot more plasmonic nanoparticles, but I think I don't really have time to tell you all about this. Maybe during the talk here and there, plasmonic particles will, appear, disappear, and so on. Yeah. So now I would like to briefly switch gears and discuss a little bit about Fabry-Perot cavities, so our second approach. And probably many of you are familiar with the fact how usually strong coupling with Fabry-Perot cavities is done. So this is a sketch here. You see, for example, two gold mirrors separated by some distance. And in this region in between the mirrors, you could put molecules, for example, or organic chromophores, which would have absorption peaks somewhere in the visible range. And then if the distance is large enough here, let's say 100 nanometers or so, then this is also simultaneously a Fabry-Perot resonator, right? And also it will resonate in the visible range. So when you match the resonance of the molecule with the resonance of the Fabry-Perot, then you can get Rabi splitting, like typical numbers with organic chromophores. You can get up to maybe 300 MeV rather easily, right? So this is like a typical spectrum, how it looks like with realistic numbers. My point is that it's actually a collective effect, right? So in order to get that, just like what I was speaking in the previous slide, you need to get the square root of n effect, collective effect. So there are quite many molecules that are needed to realize strong coupling in this scenario. And on one hand, it's collective, right? But on the other hand, this collectiveness gives us freedom because these molecules, essentially, they don't need to be exactly the same, actually. They can be spectroscopically the same, let's say indistinguishable spectroscopically, but chemically it can be, let's say, two different types of molecules, A and B, for example. Those A and B would have, let's say, the same optical resonance, but they could be very different chemically or whatever, right? So that would allow you to actually construct a system which would sort of intermix different things. And this was done in literature, of course, long before us. So similar approaches of intermixed polaritons were actually introduced already in the 70s by Acknowledgement, where he used Frenkel excitons in molecular structures and Vannier-Mott excitons in solid-state structures to realize these intermixed polaritons, Frenkel-Vannier-Mott polaritons. Actually, there are also many similar concepts where people use donor-acceptor pair inside the cavity and intermix them. This was done by many authors, including some of the, probably some of the people in the audience here. Then maybe you heard about this co-hybridization concept with solvent molecules, which Thomas Ebbesen group has introduced. And what we have done in this work, we essentially went a little bit further, perhaps, and even kind of reduced it to absurdum in some sense. We've kind of removed part of these molecules and replaced them with the plasmonic particles, okay? And what we could do by tuning the plasmonic particles size and shape, we could get their plasmon resonance to actually spectrally match exactly the resonance of the molecules. And in this case, you would obtain the same Rabi splitting here, but with much, much smaller molecules, and mainly the oscillator strengths for this sort of splitted spectrum here would be provided by plasmonic particles. Okay, so this was actually experimentally then realized in a structure consisting of two gold mirrors and a plasmonic nanoparticle array fabricated by e-beam lithography. And then what we could also control, we could control the density of plasmonic particles per unit area. And that density essentially resulted in a nice knob by which we could control the splitting here. So this splitting can be actually easily, really easily achieved in the hundreds of milli electron volt range and even up to electron volts range. In fact, it turned out it's actually rather simple to reach ultra strong coupling. There was even a Nature paper from a couple of years back from a German group where they even realized deep strong coupling with structures similar to that. Okay, so plasmonic nanostructures have very, very high oscillator strengths, and then realizing this kind of split spectra is not a big deal. In fact, this was previously done by groups of Harold Giesen and famous Coendering previously, maybe in a little bit different context, but still very similar, I would say. So we could control this Rabi splitting then very precisely and very easily with the pitch between the plasmonic structures. Right, and actually, in general, we really liked this idea of using Fabry-Perot cavities and plasmonic nanostructures. Not really because it is some kind of interesting quantum system. It's not really quantum system at all. It is fully quantum system, fully classical system in a sense. But we really believe that it's an interesting model system, because what you can really easily do in this system, you can easily control the density, the oscillator strengths, and the symmetry of plasmonic particles that you use, which you put in between those mirrors. So it can be a nice platform which could allow to model stuff, look into, let's say, ultra-strong coupling regime, looking at the chirality, looking into vibrational strong coupling. And this is what we have done here in a series of works. Here, for example, we used a very high density gold nanorod array, which we packed very, very tightly here with the gaps between the particles approaching 30 nanometers or so. And in this case, we could really go into ultra-strong coupling regime, and ultra-strong coupling regime is something which is rather, let's say, attracts quite a lot of attention at the moment due to reasons related to ground state energy modifications and things like this. I will a little bit speak about this further. Then we could also easily control the symmetry of the structure. For example, we could turn it into a chiral object like here, and then we could study the kind of polaritonic response in the case of a chiral scatterer inside the Fabry-Perot cavity. Here it turned out, of course, that the flat Fabry-Perot cavity doesn't really support chirality in a way. So it was maybe not extremely interesting study, but nevertheless, you could control the plasmonic nanoparticles and their symmetry, and I think this is an advantage here. And then recently, in collaboration with a group of Karl Borisson here in Gothenburg, we've actually tuned the plasma resonance further into infrared range and could realize vibrational strong coupling with molecules, molecular vibrations, plasma resonance in gold nanobars, and Fabry-Perot cavity altogether. Okay, so in general, I really think this kind of nice model system and something can be learned out of this. Actually, let me now briefly explain you about the fabrication procedure for such a Fabry-Perot cavity. Actually, it has some disadvantages, this fabrication procedure, because occasionally it might be hard to fabricate. It very often requires some clean room facility, and it's once fabricated, it's actually not possible to tune. It contains passive elements and stuff like this, right? So we were even thinking, despite the fact that we've looked into many structures like this over here, we're thinking, is it actually possible to prepare such cavities even in more simple way, such that it would be, for example, tunable? You wouldn't need a clean room facility for that, that it would be maybe even self-assembled. And it turned out that one way to think about this could be something like that. Imagine a colloidal solution of gold nanoflakes, which are actually very well known to be synthesized by methods of colloidal chemistry. So those can be flakes of gold, maybe on the order of 10 micron size in length and about 20, 30 nanometers in thickness. Those are very well known. They exist. Many people study plasma resonances in them and running plasmas and so on. But what would happen if actually two flakes like that would meet each other? So actually then two types of interactions can arise. Actually, a lot more interactions can arise. But for us here, we would be interested in specifically those two. So of course, typically those colloidal solutions are protected electrostatically. They are covered with ligand molecules to ensure there is electrostatic repulsion. So that's one type of force that occurs between a pair of such micromirrors, so to say. But there is also this Casimir interaction, right? And it is attractive interaction. And this is a consequence of the, in the original, at least, Casimir work. It was done, of course, in vacuum and for perfect electrical conductors and so on. But later, this was generalized by Lifshitz to real media, to finite temperatures, to real metals and stuff like this. So actually, you definitely get this attraction force. And this attraction force is not so weak, actually. If you calculate it per unit area, so pressure, Casimir pressure at a separation of 10 nanometers is actually close to the atmospheric pressure. So this is not, something which is, hard to catch or anything like this. This Casimir attraction actually really plays an important role in, for example, micromechanical systems where it occasionally can be even a problem. In our case, it's not a problem. Perhaps we could find a situation in which Casimir attraction and electrostatic repulsion would actually really equilibrate each other and then form a Fabry-Perot structure, okay? In a minute, I will show you how this actually works. But before that, I want to give a little further introduction into the topic. And in fact, this Casimir-Lifshitz forces, so generalized Casimir-Lifshitz forces, were already previously used in the literature to, for example, obtain repulsive forces and even create stable Casimir equilibria. This work, which was published in Science by the group of Xiang Zhang, they were looking into movable gold flake above the continuous gold film with an introduction of Teflon spacer in between. And then it turned out that there was an interesting balance between attractive and repulsive Casimir forces. The repulsive Casimir forces here arise because of the Teflon here, because of the Teflon layer there. It turned out that they could actually get into this stable Casimir equilibrium. In this case, they even didn't need electrostatics. I would say in experiments, it's a little bit hard to get rid of electrostatics like completely. So what they've done, they've actually worked in non-polar solvents and stuff like that to really try to get with any electrostatics, to get rid of any electrostatics. Then another work here published in Nature by the group of Federico Capasso and Jeremy Monday, they looked into long-range repulsive Casimir-Lifshitz forces. So in this case, they were using an IFM probe with a gold sphere here, then confronted against either gold mirror or actually a silica substrate, and then immersed into a liquid called bromobenzene with relatively high refractive index. And what they have seen then, that the conditions on the dielectric function in this case actually satisfying the repulsive Casimir-Lifshitz forces. So you see, in this case, when they actually measured the piezo displacement, they really saw, only repulsive behavior. Whereas when they actually worked against gold, they also saw the attraction. So against gold, it is very attractive, then even in bromobenzene. And now you can think about this situation in our case, right? And actually a stable equilibrium in our case, without any Teflon or without any immersion into high refractive index material, would really follow the DLVO-like manner. So DLVO is this potential which was actually discovered, and in relation to the colloidal stability, this DLVO potential is fairly well known. The ingredients for that DLVO potential is repulsive electrostatic forces and attractive van der Waals forces. So van der Waals force and Casimir force, they have a lot in common. In fact, the fundamental background for them is similar. The only difference is that van der Waals forces are non-retarded. And Casimir forces, they take into account retardation effects, and especially for large separation of, let's say, 100, 150, 200 nanometers, as we get in this case, then Casimir-Lifshitz formalism, of course, should be followed. So then it turns out that, this colloidal stability, that's actually how Casimir actually started working on his Casimir attraction forces. Here, it turns out that we can actually really realize the same structure here, but just in the flake, in the two parallel plate flake configuration, yes, stabilized by electrostatic repulsion and Casimir attraction. So let us consider what can happen. I show here a plot of the joint electrostatic and Casimir potential, where the electrostatic part is shown in the red curve, and it's always repulsive as a function of separation between the flakes. And then this green curve here is attractive Casimir-Lifshitz potential, right? So let us consider what will happen if we add salt to the system. And salt, what does the salt does? It screens out the electrostatic contribution here. So if there is not enough salt, then we will actually not get any stable equilibrium. You see this dashed line over here? This is the joint Casimir electrostatic potential, and it doesn't have any local minimum. This situation is essentially electrostatic repulsion dominated case, right? If we add too much salt, let's say we have very much salt, then we screen the electrostatic interaction completely, and then the total potential will be just Casimir dominated, so you will have huge attraction and they will just aggregate, right? And this is also very well known to Casimir. You know, you add salt to colloidal solutions. This is very well known. You add salt to colloidal solutions, they just flop, they aggregate. But if you add just enough salt, then you can get this situation in which electrostatics is screened enough, but Casimir still doesn't dominate. So you can then create this kind of stable equilibrium here at a distance of about 150 nanometers, which would then satisfy the conditions for the Fabry-Perot indivisible range. This is kind of cool, nice prediction, right? So let's see how this looks in the lab, right? And to maybe some experiments, the lists are here. I think you maybe would like to visualize how this actually looks like. So we actually looked at just the color of the transmitted light against a static mirror. And we start with this case when we don't have enough salt, right? In this case, a gold flake actually really dances around the static mirror, and it gives you all these crazy colors in the between. You know, it doesn't form any stable potential over here. So this is this electrostatic dominated case. Now, if you add too much salt, then this is what happens. The flake just sticks to the static gold mirror. It has this black color because it stops being transmitted. The total thickness of gold becomes too much, and it actually even doesn't diffuse so much. Actually, I don't know what's exactly the equilibrium distance. Did it stack, you know, like forever there, or was the gap there on the order of 10 nanometers or something like this? Nevertheless, in the optical range, it was not visible, but maybe still is something quite interesting which people could look at. And then when we add just enough salt, it turns out that we can get this red color, for example, in much more stable situation. Or if we then add even more salt, then we could get this green flakes, okay? And they would be totally green, keeping the same distance between the flake and the mirror, and it would really then represent kind of a structure which is a Fabry-Perot cavity in water solution at room temperature, right? More to that, then it turns out that if you start playing with the static mirror and actually reduce it in size, this is what we have done actually. At first, we have prepared those tiny static mirrors first, and then we saw that all our flakes like to bunch around those static mirrors. But then we went even further. We thought, okay, but actually, do we really need a static mirror? There is enough static mirrors around already because you have a lot of flakes flowing around, right? So what would happen if they actually meet each other? So when they meet each other, this is what happens. Here you can see two flakes, one triangular, one more like hexagonish flake. When they find each other, they found really stable structure, which is actually stable both horizontally and vertically. It doesn't want to leave neither in the horizontal direction nor in the vertical direction. The resonance is obtained in the visible range, which we can easily monitor by reflection spectroscopy. We can even do the dispersion of this resonance, and we see that it shows the typical parabolic behavior for a flat Fabry-Perot structure. It's really easy to make. In fact, it's self-assembled. You don't do anything, it just forms, okay, by itself. You don't do anything, you just need to add a little salt such that you stabilize it at the right frequency range. Then you can actually tune it actively. You can control it by salt concentration, you can control it by temperature, you can control it by light pressure, for example. This is what we have done in our studies. You can see several different colors were obtained just changing the salt concentration. So one could then ask a question, okay, you now know how to prepare the cavities. Would you like to make polaritons out of this? Because you've been telling us all about polaritons. And yeah, kind of you can do self-assembled kind of trivial polaritons. In this case, the sort of trivial polariton here consisted of 3 flakes. Actually, it turned out when 3 flakes find each other, they still form a stable trimer in this case. And actually, the spectrum of the trimer looks like it has kind of a splitted type of behavior here. You see kind of 2 modes appearing. And this actually corresponds to symmetric and anti-symmetric configuration of this upper and lower Fabry-Perot structures, and the gap between them, the splitting, actually is determined by the thickness of the middle mirror, okay, which we have modeled theoretically. So when we made this mirror thick, very thick, 70 nanometers, so it was not transparent, we just recovered an individual Fabry-Perot resonance in the top and bottom structure. But as we made this mirror more and more transparent, we actually open up the splitting, and then we realized the splitting comparable to the one in experiment. So actually we can read out from here that the thickness of the mirror in our case is somewhere on the order between 20 to 30 nanometers, okay? But in theory, we can give it even further. We can make it 10 nanometer, 5 nanometer, 1 nanometer, and then eventually 0 nanometer thickness. Yeah, and in 0 nanometer thickness, it actually reduces to the first order and the second order Fabry-Perot mode of this giant, this kind of Fabry-Perot structure formed by upper and lower mirrors, right? So this is kind of the limit of, so to say, Rabi splitting that you can get in this trivial polariton picture. Then we went even further and actually used the real material, in this case WSE2, which supports excitons in about 1.6 electron volt range. And we've mixed it up with this Fabry-Perot structure. In this case, we used one movable mirror here with the top gold film, top gold flake, and the continuous gold film on the other side, right? So we have modulated that system then with a laser light on top, just with a light pressure. And this was modulated here periodically over here with a few hertz. So we first have modulated the empty Fabry-Perot cavity, and we could tune the the Fabry-Perot resonance in this range, actually moving the cavity up and down as much as about 20 nanometers up and down. Okay, actually, we have also analyzed how the unmodulated cavity would look like, and the average thickness was then on the order of 177 nanometers with the standard deviation below 2 nanometers. So it's actually a really, really stable system, turns out, which perhaps can be used for sensing applications, for other things. It's actually fun that self-assembled structures are so stable. But then when we put the WS2 in the middle, we actually realize polaritons, right? So we see Rabi splitting over there. But now, by applying the modulated laser light, we can actually tune the Fabry-Perot resonance in and out from the resonance with the WS2 exciton. And actually, if we look into upper polariton fractions, Hopfield coefficients over here, we could see that depending on the time, so depending on the modulation of the system, we can either get a nice 50-50 mix between exciton and photons, or occasionally we can really completely separate them and to make upper polariton fully exciton and zero photon-like. So the lower polariton situation would be reversed. So what it allows us to do, we can create the self-assembled structure, self-assembled polariton, which can then be actively modulated by light to go in and out of strong coupling regime just by laser pressure and by light pressure. I think this is kind of interesting. Actually, this system opens a lot of kind of possibilities, maybe together with what I told you before about plasmonic structures, ultra-strong coupling there, and stuff like that. We believe this can be an interesting platform for studying polaritons and their influence of, on material properties and maybe related topics. But here it kind of unites also with self-assembly and these kind of topics with nanomachinery and stuff like this. I think it's kind of interesting study, and we were lucky that both reviewers and editors were kind of also thinking that this is interesting. So this just appeared recently in Nature. So now, actually, depending on time, probably I need to speed up. Yeah, so I would like to speak to you now about the third part and the self-coupling, and I would like to introduce here the 2D materials, right? So switching gears a little bit. I think monolayers of TMD materials like WS2 and MOS2, something like this, are well known. They have excellent excitonic properties. Actually, there is a whole community working on excitons of them, and people like them in strong coupling community because we can use them to realize polaritons in various platforms. It was done by Vinod Menon, Tartakovsky, Schneider, Zhang, many others. In plasmonics regime, Peter Norlander, Hongxing Xu, our group, Nicholas Stenger, worked on individual plasmonic particles and TMD materials. We even did it with trion structures. So this kind of exciton properties are well known in these materials, I would say. But then we also went a little further and we speak about multi-layer TMDs. They are a bit less of work. Jeremy Baumberg group has this nice work on multi-layer TMD in the gap between his particle and the film structure. We worked with individual this bipyramid antennas, where in this focus of this nano antenna, we could position this TMD material. Long story short, what I want to say about this is that in multi-layer structures, despite the fact that the indirect band gap, one could see strong absorption on one hand, But on the other hand, very high refractive index, very high refractive index. And just to give you the numbers, yeah, as I said, TMDs have unique excitonic properties, which is well known. But maybe a little less known is that their optical properties are also great. They have very high refractive index. Background refractive index is bigger than 4. That's actually bigger than silicon and gallium arsenide, which is used for high index dielectrics. Okay, so they can perhaps be used for high index dielectrics. Also, they are very anisotropic. The parallel and perpendicular component contrast is on the order of 1.5, which is a kind of obvious consequence of the van der Waals nature of these layered crystals. And this is also maybe something nice. Perhaps one could use this for high index TMD nanophotonics. And in fact, my group is actually working on this. But in the context of this talk, it can be used for this cavity-free polaritons, where an optical mode can be confined by the material itself, by the high refractive index of material itself. But since the material also has excitons, you can hybridize the system. And in this case, we have hybridized it with Fabry-Perot modes of the slab. And in this work, we have hybridized excitons with the Mi resonance of a nanodisk. Okay, so maybe, yeah, references can be found here. Maybe to discuss it in a little more detail, I would like to explain this self-hybridization concept in the TMD flake. Okay, so imagine you have a slab of TMD material with background index bigger than 4, and you place it in vacuum. Then, just because of the refractive index mismatch at the interfaces, you will support Fabry-Perot mode here, right? But then, as you tune the thickness of this Fabry-Perot mode, you might find yourself in the situation where you tune this cavity mode shown here in green exactly to overlap spectroscopically with the exciton position. And when you do that, you hybridize those modes. So you obtain kind of polaritons in the system for which you actually don't need an external cavity. You just realize those polaritons in the slab itself. So this is how we've done this in experiment. We first have recorded reflectivity spectra dispersion for these 4 most standard TMDs in the range of thicknesses on the order of 10-20 nanometers. And here, all the dispersion was flat. We just saw regular A, B excitons, nothing else that was flat. And this is probably was because this cavity mode was too much in the blue because the thickness was too thin. But when we made the thickness thicker on the order of 60 to 80 nanometers, you then recover this very standard, let's say, polaritonic looking like structures with parabolic dispersion and stuff like this. So the sweet spot in thicknesses turned out to be on the order of 60 to 80 nanometers, depending on the TMD material. And we really could then realize Rabi splitting here on the order of 200 MeV and so on, which is quite nice in a structure without a cavity. So maybe this is interesting for polaritons, right? And then we have realized it in other structures. But maybe, to speak even a little bit further than this, I would like to tell you that, now you know that excitons in TMDs, these are very nice structures. A lot of people study them. And I told you that it has interesting optical properties, refractive index bigger than 4, excitons, self-hybridization, stuff like this. But then another degree of freedom which you really can control in TMD materials is actually their edges. So once we were working on these TMD structures, actually on holes of these TMD structures, we actually almost by mistake realized that we can really control the edges of this material in a very nice way. For example, the edges of these materials are not to be zigzag or armchair, right? And zigzag edges are actually the interesting ones because they have very high catalytic activity for hydrogen evolution reaction, for example, for water splitting, for oil hydrodesulfurization, stuff like this. But they're also simultaneously metallic. They've been shown to be metallic and improve electrical transport, both theoretically and experimentally. So what we have done, we have fabricated an individual hole in this TMD material by e-beam lithography, and it was round in the beginning, okay? But after exposing it into anisotropic wet etching, which was just a water solution, aqueous solution of hydrogen peroxide and ammonium, nothing else, very, very simple chemical. In a matter of a few minutes, we were able to control this circular hole into a nicely looking hexagon. And in this hexagon, the edges were really all zigzag. They were really dominated by zigzag. Then we were doing this high resolution TM and SEM images. We saw this really, really sharp structures, right? So actually what happens here is that our chemical removes all the unwanted edges because they are likely non-stable. against chemical etching, but it leaves the most stable edges, which turn out to be zigzag. And then we looked at them in a high-resolution TM microscopy together with Andy Youngers and Eva Olson here at the Department of Physics. And we saw that those edges in the hexagons, they are really, really sharp. Okay, they're actually very close to atomically sharp zigzag edges, and zigzag could be visualized here by electron diffraction. Moreover, we have performed electron energy loss spectroscopy here at the very edge of this TMD material, and it turned out that we reconstruct A, B, and C excitons. So we actually show that our etching technique is not damaging excitons at all. Our structure is really nice, kind of self-limiting etching structure where you get nearly atomically sharp edges with zigzag, which are useful edges, as I said, for transport properties, for catalysis and so on. So then we went even further and we have fabricated nanostructured Emd arrays with these atomically sharp edges. And we could do it with really large areas. Actually, right now we can even do it close to wafer scale. And previously we started with exfoliated flakes, and now we continue towards CVD. So we could do it in large areas like hundreds of microns. It was very, very reproducible. It's simple. It works in a very wide parameter range. And we can even control this new degree of freedom here, array lattice versus the crystal lattice. So hexagon actually follows the hexagonal lattice of the TMDC crystal, while the array lattice allows us to control and get different structures here, ranging from, for example, honeycomb structure, this kind of bow tie structure and vertex structure in the middle. And all of them still have sharp zigzag edges, nearly atomically sharp, okay? Moreover, because the control is so high, yes?
Is the 45 minutes you told me?
Yes, I'm almost done. Thank you. Thank the nano junctions here also on the order of 3 nanometer. So this already is in a quantum size regime because the Bohr radius of excitons in these materials is actually on the order of 1.5 nanometers. We can realize structures on the order of comparable to the exciton Bohr radius, which means that actually in these structures we could expect interesting quantum size effects. And we are currently actively looking for those effects in these structures. But actually, I would say this is like cool structures. What we've then done, actually, since we speak about optics a lot, we looked at the optical response. So what you see here is an array of these edge structures taken in just a regular optical microscope colorful photograph. So we can actually get, with your bare eye, actually, you can see this blue, green, yellow, whatever colors, which are just a function of the thickness of the ribbons that you are using in this structure. And all of these ribbons are still atomically sharp with the zigzag edges. And you can even see by measuring reflectivity, and you can get this, reconstruct this anti-crossing of the two modes around the exciton band of this TMDC material. Okay, so it's actually beautiful colors, beautiful edges at the same time combined even with polaritons in this structure. Okay, and maybe just to finalize this talk, like in the few remaining minutes, I want to a bit generalize this and say, this self-hybridization approach, what I told you now is mostly about TMDs, right? We spoke about disks, we spoke about, slabs and stuff like this. But of course, it's probably not limited to TMDs. So all you need to have a strong enough transition there. It can be exciton or phonon, right? Or even molecular vibration. And then you should have a background index which would form you the mode, right? And there are actually very, very many materials with strong transitions. One of the simplest material you can think about is liquid water. Actually, liquid water has a huge absorption in the infrared, which is a result of, actually it's even known that water vapor is a greenhouse gas, right? It absorbs much more than CO2, for example. And where would you form nice structures which would support me modes? Well, just in clouds, okay? In clouds, steams, fogs, or, if you go to this wet saunas, where you don't see much, this is because there are beautiful water droplets there. And these water droplets look like this. They just form automatically because of surface tension. The funny thing, is that actually in clouds, the average size of the droplet is on the order of 10 to 20 microns. The funny part about it is it's actually simultaneously like a bottleneck. because droplets smaller than 10 microns, they diffuse very much. And that's why they collide very much and form bigger droplets. Droplets bigger than 20 microns, they are too heavy. So they fall because of gravity, actually in the form of rain. You know, you get rain in the end. But 10 to 20 micron droplets, funnily enough, this is a bottleneck because they are neither in the diffusion regime, they are too big to diffuse, but they are still too light for gravity to be important. Actually, it's a funny, even open problem. I didn't know about that, but I chatted with atmospheric person here who told me this story. So the funny thing is that this 10 to 20 micron size is exactly the size range in which the me modes and even whispering gallery modes in this water droplet will overlap with the huge absorption of water vibration, okay, water molecule vibration, okay? So what we do, we actually look at this water, which has high oscillator strengths in mid-IR. We look into water droplets which support me modes in this size range of few microns. And many of those exist naturally, as I said, for example, in clouds. And then we look into this vibrational me self-hybridized polaritons, even in the ultra strong coupling regime, because water has like huge absorption, right? So technically we follow this, we search for polariton eigenmodes in the complex frequency plane as roots of corresponding dispersion relations. Because it's a macroscopic body, we of course use the epsilon approach here, and the simplest one we can do is the Lorentz function, okay? And then this is roughly how it is in the complex frequency plane. So you just saw two different polaritonic bands appearing and never crossing each other, right? So this was published in the JCP by Adriana Canales, the first author. She really did that beautifully, technically. In fact, as I told you already, this was done before, long time before us. This was done by Hopfield in his beautiful work in Physical Ref in 1958. So he actually just realized this bulk, so-called bulk polaritons in unbound excitons, like in the three-dimensional space filled with excitons. And there, what one could get the strong coupling regime, one could get weak coupling regime where they cross. One can even get ultra strong coupling where the kind of polaritonic gap opens up. This is all just a question of the corresponding dispersion relation and the strengths of the oscillator which you put in your Lorentz here. Okay, so this is very well known from Hopfield, 1958, right? Maybe what is a bit less known is that if you then start reducing dimensionality, you can realize these polaritons in slabs. And I showed you already the slabs of TMD materials, but you can also do it in J aggregates and HBM, for example, in correspondingly visible range and infrared range. And you can get it above the light cone, below the light cone. You get these all polaritons, which are well known, right? Even this kind of polaritons below the light cone, they're also very well known, studied by Snom, for example. People look at them like that. Then polaritons in cylinders can be realized as well. If you reduce dimensionality even further, for example, you can consider the perovskite nanowires. A typical example is cesium, lead, bromine, or even better, fluorine wires. They support the same kind of polaritonic bands, both above and below the light cone. And then finally, you can look into water droplets, okay? And water droplets support this really nice me modes now in the size range of a few microns over here. You get this nice anti-crossing here around this 0.42 electron volts where the water vibration happens. And you get this splitting, which is actually even in the ultra strong coupling regime, because the G over omega here is more than 10%, in fact. So it also turns out that if you start looking at the extinction cross sections of those water droplets as a function of size, then this is a sweet spot where you do see this splitting over here between the modes. So these are these polaritonic modes which I told you about in clouds. But if the droplets are made smaller, for example, smaller than this 1 micron, then you actually fall in the regime where they stop being polaritonic, okay? So actually, the size of the droplet may determine whether you are in this polaritonic regime or not, which is maybe interesting. So with this, I want just to say that actually polaritons turn out to be much more abundant than at least I thought originally. Yeah, they're actually virtually everywhere around us, even in clouds. You know, if next time somebody tells you, okay, I work on polaritons, why should you care? or like, why should anyone care? You can actually say to them that, you know, water droplets in clouds actually are polaritonic, nicely polaritonic, just the right size range, right mean resonance, right absorption coefficient for water, right? Another thing which is kind of nice out of here is that the maximum splitting that you can get actually depends on material itself. Okay, it doesn't depend on the cavity. It mainly is the parameter of the material itself, and it is very easy to estimate. In fact, the maximum this bulk polaritonic splitting G is actually given just by the plasma frequency, oscillator strength, and background permittivity. Okay, this number is the maximum splitting that you can get for certain material. And this is very easy one-string calculation. I think, especially for experimentalists, this is nice because sometimes I get a lot of questions like, oh, you know, this material is good for strong coupling or not? Is it good or not? You know, I mean, this is the answer. You know, you can do the calculation, just fit your dielectric function with Lorentz, do this calculation. If you're happy enough with the G that you get, then go for it. If you're not happy, then this will never, ever bring you to the Rabi splitting that you like. Moreover, I would also like to highlight that these bulk polariton effects that we consider here, they are intrinsically collective, right? We've been treating this with epsilons everywhere. And actually, you know, collectiveness is rather hot topic, I would say, in this polaritonic chemistry and things like this. People very often question these collective effects, right? I would say all of these polaritons, which kind of bulk polaritons in a way just confined to different structures, they are all intrinsically collective. Okay, so maybe this is something. But then something that I really don't understand is, okay, these polaritons are there. They are eigenstates of the system, right? They naturally happen in myriads of structures around us. Are these polaritonic states what relevant, you know, for anything? For example, for polaritonic chemistry or exciton transport or other cavity-related phenomena, are they interesting or not? This is what I'm trying to understand. This is kind of a bit open question for me. And what are really the differences between them and more, let's say, standard cavity polaritons? And, you know, if yes, then in what way are they relevant? And what are the differences? And if no, then I also want to understand why they are not relevant, for example. Actually, they are still the same solutions. So eigenstates of the system, right? And they are polaritonic and they are collective and so on. Dark states will also exist there and so on. So I'm kind of freaked. Anyways, this brings me to conclusion. I've roughly divided the talk into two parts where we discuss cavity and cavity-free polaritons. Here we discuss small plasmonic structures, then plasmonic particles in the cavity, and then even self-assembled cavities. And the cavity-free, we were talking about slabs, talking about disks, talking about the edges, and even water droplets in clouds. Okay, with this, thank you again for your attention. And just like to mention that these edges, we actually patented that, and that's what the company is all about. So if you're interested here, maybe, I don't know, if you don't want to fabricate it yourself, but you're interested enough to look at this, maybe you can just buy it from us. Antonio, I hope it's okay. Yeah.
Thank you very much, Timur. We are a little bit over time, so let's. I mean, if you have any question, and anyone in the audience, you can just unmute yourselves and make the question as quickly as possible, so that we don't go much later.
May I ask a question?
Sure, sure.
First of all, I would like to know about these crystals you made of these holes, like arrays, or how do you call it?
Yeah, this one.
Yeah, I would like to know how large you can produce fresh materials. I mean, in microns, 10 microns.
Yeah. So those original flakes that we used here, they were originally exfoliated flakes, and they were multi-layer flakes. It's actually not a monolayer. That is something that I have to mention.
Oh,
so
okay.
The flake dimension can be exfoliated flakes of this thickness can be on the order of 200, 300 microns. So 203 microns, 200, 300 in X, and the same in Y, roughly. Yeah, and then we can pattern the whole surface, just the whole surface. So it's kind of macroscopic. You can see it by eye. Yeah.
So it's more or less like have equal size in 3 dimensions, yeah?
Yes, yes. And then actually right now we are expanding this with a CVD method to even bigger. Actually, it doesn't seem to have any limitation in terms of lateral size. In terms of thickness, actually we went all the way. Let me actually try to show this. In thickness, we've been going, let me see if I have this back slide. So in thickness, we have actually tried to go all the way to monolayer. And actually the funny result was that these hexagons still appeared in the bilayer, but not in monolayer. So there is something funny about monolayers and bilayers. We believe that the consequence of this hexagon structure is actually the 2H structure of WS2 multilayer. So it's this AB stacking, and it's kind of an overlap of 2 triangles rotated by 180 degrees. That's what gives you the hexagon. But in the monolayer, you don't have it. So monolayer is a bit special. And actually, we know how to produce monolayers with hexagons by just exfoliating the thicker crystals. But maybe something to highlight here is that sometimes it's actually interesting to look into monolayer physics instead of monolayers. Sorry, multi-layer physics instead of monolayer. For example, in our case, these hexagons would not be discovered if we were working with monolayers, which a lot of people do work, but we work very often with multi-layers for many reasons. For example, this photonics that I mentioned. Yeah?
So does it mean that, okay, maybe final question, but this you can produce these nice holes only for even numbered layered materials, yeah? I mean, for free layer you cannot produce those holes.
Actually, we tried 3, 4, 5, 100, 150, whatever. Then it went to macroscopically. Actually, on the thicker level, there seemed to be no restriction at all. So even for 3 layers, for 4 layers, for 5 layers, we still can produce it. Actually, why it is not exactly known to us, I would say. But we suspected that this is related to the 2H AB stacking structure. Yeah? However, this is something to be maybe verified.
And as I understand, you can produce, you can control the like the structure. I mean, I see here the 4 different types of, like, let's say, crystal structure or array structure. You have like pure hexagons, then you have like distorted hexagons, and finally you have like how it's called, the last one.
Yeah.
Okay. Okay. So sorry to interrupt you, but let's try and move to a second question, and you can talk later.
Pardon.
Okay. Yeah, no problem.
Okay, so if I mean, we are a little bit over time. So we have time for a last question, if anyone wants to do it. And if not, I do have one. And it's about this. I mean, what are polaritons useful for? No, the last question that you launched.
Yes.
There are some studies that claim that they are good for sensing, and I was wondering if in your flake nanocavities, where you can see a strong coupling, if you see any higher sensitivity when you have polaritonic resonances than when you have just normal optical resonances. Is this something you support, or you don't think this is a real statement?
Actually, Antonio, maybe I can rephrase your question briefly, because I think there is this archive paper now with a lot of people from Cambridge, where they look actually at cylinders and some kind of either J aggregates or some kind of molecular chromophores. So I think they claim the same regime there, polaritonic regime between wire modes and the excitons in those molecules. And they claim this is actually good for exciton transport. So maybe you have seen this work. Yeah. Actually, this seems to be kind of reasonable. I even remember many years ago discussing this with Johannes. Johannes, back then, if I remember correctly, he was not too inspired by this somehow. But nevertheless, surprisingly, I saw this paper. This is nothing that we have done. Okay, we've just looked at this, into TMD slabs, but then we really like these water droplets. But concerning sensing, I mean, maybe I can briefly tell to you with TMDs. I think, like, I'm not sure what do you mean really by sensing. What I think we saw. Maybe you can comment.
Yeah. Okay. No, I mean we are really over time, so I can explain you. I meant about the salt and the salt quantity, but I mean let's talk about it later. So
okay. This is something that I didn't think about. Okay, sorry. But maybe we can take it. Maybe we can take it later.
Let's finish here so that people can go for lunch. Thank you very much, Timur, for the very nice talk on many topics, all of them really interesting, and the very interesting results too.
Yeah, so sorry for taking too much time. Really.
No. You are enthusiastic. You want to present